Hello everyone, this is Aerospace and Aerodynamic Training course from ANSYS Fluent Training Course Series. In this session we are going to discuss about the basics of the aerodynamic and why we need CFD in our aerodynamic related projects. So the outline for this course will be first discussing about lift force and coefficient determination, and next about drag force and coefficient determination, moment and moment coefficient determination, and type of shock waves and shock wave determinations in aerodynamic projects. So the first question we are facing in this course is why we need CFD to use in our aerodynamic related projects. The answer is quite simple. From early 1960s and 1950s, the NASA and other related companies in aerospace industry realized that they need a tool to determine the flow movement around their airplane and carrier missiles. So they start to actively using CFD methods and CFD codes to determine the flow path over their objects. First, it wasn't that much accurate model, and by passing time, now in the beginning of the fourth industrial revolution, we have a big ability to simulate everything quite exact with experimental values. So as you imagine, we have, for example, an airplane or missile or a car, and it goes very fast and facing a flow that is drag force is really matters, like Formula 1 cars or high-speed aerobatic airplanes. We need to understand how this drag generates, what effects on the drag generation, and how our lift distribution will be, how our vortex generation will be. And as you know, probably the vortex is one of the key elements that we are going to investigate on the designing of the wing of aircraft. We need to see where the separation occurs, and we use a tool such vortex generators to create a vortex to avoid that separation. So now from beginning of this course, with the help of ANSYS Fluent software, we are able to simulate simple aerodynamic problems to really advanced aerodynamic problems, such as fluid structure interface, or even we can determine our airplane and our aerial object dynamic stability derivatives from CFD. And we want to go on to see what we can do. So as you know, in CFD we are facing numerous equations that we want to solve over our objects. These equations are mostly PDEs, such as Navier-Stokes equation, and there is no exact solution for these kinds of equations. So we need to use our numerical method to calculate the values of these equations in each cell zone. And so to do that, we need to generate a mesh grid for this computational process and simulation. So now we are facing, as you see, one of the important equations that we are facing in aerodynamic. This is a Navier-Stokes equation. Navier-Stokes equation is the basic and literally the cornerstone of aerodynamic. With this equation, we are able to solve our flow path and determine the pressure and density change and temperature change along our object in the space and in every aspect of it, and we can even extract other properties to see what's happening actually around our object. So Navier 6 contains three equations for x momentum, y momentum, and z momentum, and it contains with continuity equation also to solve continuity. If we are facing a compressible flow, the energy equation will add to these four equations and will round up to 5 PDs that we need to solve in our domain to reach the solution. So now we get to the first main question: how lift generates. So as you know, the lift is generated by the difference of the velocity between the solid object and the fluid, and there must be a motion between the object and the fluid, so no motion, no lift. It makes no difference whether the object moves through a static flow or the flow moves past a static solid object. Lift acts as perpendicular to the motion. So lift is in the force that holds an aircraft in the air. Lift can be generated by any part of the airplane, but most of the lift on a normal airliner is generated by its wings. Lift is an aerodynamic force produced of motion of the fluid past an object. Lift acts through the center of the pressure of the object, and it's defined to be a perpendicular for the flow direction. So there are many explanations for the generation of the lift found in encyclopedias and in the basic physics textbook and on websites. But unfortunately, many of the explanations are misleading and incorrect. Theories on the generation of the lift have become a source of great controversy and a topic for hot arguments. Lift occurs when the flow of a gas is turned by a solid object. The flow is turned into one direction, and the lift is generated in the opposite direction. According to Newton's third law of the action and reaction, because air is a gas and the molecules are free to move about in a direction, and the solid surface can deflect a flow. For an airfoil, both the upper and lower surfaces contribute to the flow turning. Neglecting the upper surface part is turning the flow leads to the incorrect theory of the lift. So we can now understand that no flow means no lift. Lift is a mechanical force and it's generated by interaction and the contact of the solid body with the fluid. Liquid or gas, it is not generated by a force field. In this sense, a gravitational field or an electromagnetic field cannot generate lift, and the object can affect another object without being in physical contact. For lift to be generated, the solid body must be in contact with the fluid. No fluid and no lift. So there's a difference. The space shuttle does not stay in the space because of the lift from its wings, but because of the orbital mechanics related to its speed, and speed is nearly a vacuum, so without air there is no lift generated by the space shuttle wings. So how the Fluent calculates the lift force then? So all the three aerodynamic coefficients are integral of the pressure coefficient curve along the chord for the airfoil. The coefficient of the lift for a two-dimensional airfoil section with a strictly horizontal surface can be calculated from the coefficient of the pressure distribution by integration, or calculating the area between the lines on the distribution. And as you see, we have the expression is not suitable for direct numerical integration using the panel method of lift approximation. And the panel method is the way we use in the past years, like early 70s, by using simple source flows like sink source and vortex to model and approximately estimate the value of the lift. But now by CFD methods we can exactly calculate the value of the lift around the wing itself. So this is not suitable for the direct numerical integration using panel method of the lift approximation, as it does not take into account the direction of the pressure induced lift. This equation is truly only for zero angle of attack, and it can be measured by going to higher angle of attacks by using pressure distribution. So as you see, we have our constant in the still equation, and these constants, as you see, are marked in green and blue rectangles, are input to our reference values inside software, and we need to manually edit them because the pressure only reads the pressure coefficient and does not have access to these values such as areal length or reference density of the air. However, it can calculate the density change along the domain or change it over the surface of the airfoil or aircraft, but we need to give it the reference value in this box. So the next question is how drag generates. So we think of drag as an aerodynamic fraction, and one of the sources of the drag is skin fraction between the molecules of the air and the solid surface of the aircraft. So the fraction drag coefficient is used for the characterization of the friction drag, which is caused by shear stress. The friction drag coefficient CF puts the wall shear stress tau omega in related to the flow velocity of the undistributed external flow, as we know V infinity T. The flow velocity is expressed by the dynamic pressure of the undistributed flow. Note that both quantities have the same units and the quotient is there. So as you see here, we can divide our drag force into three components, such as parasite drag, lift induced drag, which is CDI, shown by drag induced by due to the lift force, and we have wave drag, which generates by the shock wave. So for the lift induced drag and the wave drag, we can have very accurate models, but for parasite drag, for example, this won't be easy to calculate it itself generally, because we have interface drag and profile drag, which are not really that much independent from each other. For example, for interface drag, in the aircraft body, we have a fuselage and we have a wing. Fuselage for itself has its own vortexes and has its own vortex generations and extras. For the wing, we have fraction drags. We have its own interfacial drag with all the components like pylons. And when these two components, fuselage and wing, are joining together in the root of the wing, we have these two streams connected and interfaced with each other, and we have interface drag here. So you can actually divide to see how much this portion of the drag for the wing and how much portion of this drag is for fuselage itself. So for example, for skin fraction drag, we can apply the sense of skin fraction drag by changing the roughness of our surface, our wall. But this roughness for the wall is just a constant, and it's not actually modeling the roughness distribution on the wing. For the pressure drag itself, we can see the pressure distribution, but this is just a force and not the stream related. So we can see the parasite drag, however, pretty accurate, not that much accurate, but pretty accurate in the summation of these three drag divided forces. But we can calculate it individually to see how much is this. So the parasite drag, lift induced drag, and wave drag can be summed together and return us total drag force here. So now, what's then the moment of coefficient? The moment coefficient is a value of the tree, and it means in the aerodynamic that the pitching moment on an airfoil is the moment or torque produced by aerodynamic force on the airfoil itself, if that aerodynamic force is considered to be applied. Not at the center of the pressure, but at the aerodynamic center of the airfoil. As you see, center of pressure is the place that all the pressure distributions can be neglected there, and the aerodynamic center is different from center of pressure. Aerodynamic center is the point that all the aerodynamic forces are applied there, and at that point our pitching moment equals to 0. So the pitching moment on the wing of an airplane is a part of the total moment, and that must be balanced using the lift on the horizontal stabilizer. A pitching moment is any moment action on the pitching axis of a moving body. So the lift on the airfoil is a distributed force that can be said to be act at the point called the center of pressure. However, as a angle of attack changes on the cambered airfoil, there is a movement on the center of pressure toward the aft. This makes analysis difficult when attempting to use the concept of the center of pressure. One of the remarkable properties of the cambered airfoil is that even though the center of pressure moves forward and aft, it in the lift imagined to act as a point called the aerodynamic center. The moment of the lift force changes in proportion to the square of the airspeed. If the moment is divided by the dynamic pressure, the area, and the chord of the airfoil, the result is known as a pitching moment coefficient. This coefficient changes only a little over the operating range of angle of attacks of the airfoil, but the change in the moment slope against the angle of attack shown in the figures, which are available in the aerodynamic books, if you search about them, seems very steep. So this should be a change in the pitching moment of the wing about CG rather than the AC. The combination of the two concepts of the aerodynamic center and the pitching moment coefficient makes it relatively simple to analyze some of the flight characteristics of the aircraft, such as when we have dynamic stabilities can be calculated with CFD, that we are going to discuss them in sessions ahead. So the moment and the pressure relation is about that a cylindrical wing section of the chord C and the span B has a force components A and L, and a moment of M for our moment. For the moment origin of leading edge is the moment has related with the pressure as below you see in the equation, and somewhat less occurred, but it's still common occurrence as below as you see. So what does Fluent is it asks you to give a coordination for the center that you want to calculate the moment, and you give a number, and it also uses again a pressure integration to extract the pressure distribution, and using that pressure as a force and undistributed force, it calculates the torque moment around that point is given by you. So in physics, a shock wave is a type of propagating distribution that moves faster than the local speed of sound in the medium, like as flow, airflow, or water itself. Like an ordinary wave, a shock wave carries energy and can propagate through a medium, but it is characterized by an abort, nearly discontinuous change in the pressure, temperature, and density of the medium. For the purpose of the comparison, in subsonic flows, additional increased expansion may be achieved through expansion fans, also known as a Prandtl-Meyer expansion fan. The accompanying expansion wave may approach and eventually collide and combine with the shock wave, creating a process of undistributed interface. The sonic boom associated with the passage of the supersonic aircraft is a type of sound wave produced by a contracting interface. When an object or moves faster than the information can propagate into a surrounding fluid, then the fluid near the distributed cannot react or get out of the way before the distributed arrives. In shock wave, the properties of the fluid, density, pressure, temperature, or flow velocity and Mach number change almost instantaneously. Measured of the thickness of the shock wave in the air have resulted in the value around 200 nanometers, which is in the same order of magnitude as the mean of the free path of gas molecules. In reference to the continuum, this implies the shock wave can be treated either line or a plane if the flow field is two-dimensional or three-dimensional. Shock waves are not conventional sound waves, as a shock wave takes to form very sharp changes in the gas properties. Shock waves in the air are heard as a sound of a crack or snap noise over longer distance. A shock wave can change from a non-linear wave into linear wave degenerates into a conventional sound wave as it heated in the air and loses energy. The sound wave is heard as a familiar sounds as a sonic boom, commonly created by the supersonic flight of an aircraft. So, elementary of the fluid mechanism utilizing the ideal gas, a shock wave is treated discontinuously where entropy increases abruptly as the shock passes. So the normal shock wave will be simplest form of the shock waves when the speed of the traveling vehicle is equally as the speed of sound. So since there's no fluid is flowing discontinuously, a control volume is established around the shock wave, with the control surface that bound this value parallel to the shock wave, with one surface on the pre-shock side of the fluid medium on the left side. The two surfaces are separated by a very small depth such the shock itself is entirely combined between them. At such control surfaces, momentum, mass, flux, and energy are constant. Within combustion, detonation can be modeled, or the vehicle passing through the air by hypersonic speed can be modeled though. So for the oblique shock wave, when we analyzing the shock wave in a flow field which are still attached to the body, the shock wave, which is developing at some arbitrary angle from the flow direction, is termed oblique shock. These shocks requires a component vector analysis of the flow, allows the treatment of the flow as an orthogonal direction to the oblique shock as compared to the normal shock. As you see in this picture, we have some equations to calculate the pressure before and after the shock wave, and also we can determine the angle of the shock wave based on its Mach number and air density, which describes the altitude. So there is different angles related to this shock wave based on the cone angle itself and the Mach number as MN, called the normal Mach. So as you see in this picture, we have a different angles related to different angle of the nose cone or the Mach number. As you see in these equations, we can calculate the exact angle based on these theta degrees, or we can have a normal Mach number called as MN, which are available in the aerodynamic books. There's certain tables that are describing our Mach number before and after the shock wave based on the cone degree itself and the angle of the shock wave. So what does Fluent do is it calculates the pressure distribution along the lines on the domain, and by that pressure it can reaches to the places where we have a jump in our pressure, and it indicates that we have a shock wave there. So the shock waves can be reflected as light beams inside channels or ducts of, for example, aircraft intake. These reflections can occur for two main reasons. For example, imagine we have an intake for our supersonic aircraft. We want to reduce the pressure and the speed below the Mach 1 to give an undistributed air to our turbofan engine. So we can use this effect to reflect the shock waves and the flow by passing each shock wave. As you see, there is a pressure drop after shock wave. The velocity changes and drops until we reach our normal shock wave, and the flow after the final shock wave gets a below Mach 1, and we have a subsonic undistributed flow. And designing this reflection and the angles of that helps us to provide undistributed air and analyze it. So as we said in the beginning, the supersonic expansion fan is technically known as a Prandtl-Meyer expansion fan. A two-dimensional simple wave, it is centered expansion fan process that occurs when the supersonic flow turns around a convex corner. The fan consists of an infinite number of Mach waves and diverging from a sharp corner. When the flow turns around a smooth and circular corner, these waves can be extended backward to meet the point. Each wave in the expansion fan turns the flow gradually in the small steps that physically impossible to the flow to turn through a single shock wave, because this would violate the second law of thermodynamics. Across the expansion fan, this flow accelerates, velocity increases, and the Mach number increases, while the static pressure, temperature, and density decrease. Since this process is isentropic and the stagnation properties are like total pressure and total temperature remain constant across the fan. The theory was described by Theodor Meyer on his thesis, dissertation on 1908, along his advisor Ludwig Prandtl, who had already discussed problems the year before. So we have different equations in this kind of waves with other ones, but in these cases we can also estimate the value with T, P or rho, but the main difference here, we have a higher speed and higher Mach number after the expansion fan, after the expansion wave before it, as we see vice versa in the shock waves. So at the end we have a highly complicated phenomena which are cross shock waves. In these cross shock waves we can combine and interface two kinds of shock waves and expansion bands together to reach and design to our desired operational design point. So by using CFD we can calculate them without having to commonly work through complicated equations and avoiding the non-exact solutions in 3D flow.
This was the first session of the aerospace and aerodynamic training course. A further list of material and solved examples is available below. If you want to watch the continuation of this product, you can get it through the available contact channels. To benefit from MR-CFD services, including simulation, consultation, and training, visit our website or contact us via info@mr-cfd.com.